Okay. And here is the setup for sampling distributions. Let's suppose I have a sample size. Many of you did not write this. I was hoping that you would write on question number 1. The sample size is lowercase n. We've been using it for 2 months. Sample size n. Population size uppercase n. We've been doing that for a long time. Okay, so let's suppose I have a sample size of n. And I collect, let's say, BMI. Like we just did, we had a problem. Body mass index. And I have the numbers, let's say x1, x2, x3, n of them, xn. I collect on n of you your BMI. Okay, let's say I graph them. I realize that this is a normal. I do the probability plot to check, assess normality. Let's say it's normal with mean, mu, and sigma. So I know that mu is right here, and this is x, and it's a normal random variable. But now I would like to look at multiple samples. Multiple samples of size n. I go to many classes, many courses on campus, and I select the same sample size from each class, let's say 20 or 15 or whatever I select, and I determine the mean for each class. For BMI, for your class, for our class is x1 bar or x bar 1. For another class, I get x bar 2. They all have the same sample size. Okay? And then I go to the third class. And then I go to the fourth class. And I continue as long as I want. I created a new random variable. What is the random variable here? The BMI. But now I created a new random variable with the mean of the first sample, our class, the mean of the second sample, the mean of the third sample, the mean of, and so on and so forth. This is called the sampling distribution of x bar, of the mean. So I add 15 of you, their BMI, and I divide by 15, I get this number. I go to the next class, I collect exactly the same sample size, I determine their mean, divide by the same sample size, and I get, and so on and so forth. So this is a new random variable. This is the random variable that is the mean. It's not the BMI. It's the mean of each. It turns out that this is normal with the same mean as every sample, same mean, mu. But this time, the spread of the data, remember, when we talk about the spread, we're not talking about the center, is sigma, this sigma, but divided by the square root of n. Because I divide by something, the spread of the data is much smaller for this new random variable that I just created. So how does this look? It looks like this. If this is x with mean and the spread of sigma, so x is normal with mu and sigma. Here is the graph for the next distribution, the other distribution. Which one? This one, called the sampling. It comes from sampling. It doesn't come from one. It's coming from many samples. Sampling distribution of x bar will look like this. So this is the sampling distribution of x bar with normal, mu, and sigma over the square root of n, which has much less spread. How much less? Divided by the square root of n. This has this spread and this has this spread. Where do we apply this? So now let me share. Where is my book? Not my book, but my assignments. Okay. So what's behind this idea and what are the applications? Okay, so here we are going to look at as many as 18. You choose. Let's work on this.
We do that first one?
Yes, of course. Okay. Fill in the blank. Blah, blah, blah is the distribution of all values of the statistic when all possible samples of the same size n are taken from the same population.
I think it's the sampling distribution.
Of course. The sampling distribution is the distribution of all values of the statistic when all possible samples of the same size n are taken from the same population. Well done. Who would like to try this one?
Reading or answering?
Whatever you want.
I'll answer. It's true.
So the distribution of the sample mean x bar will be normally distributed. Yes, if the sample is obtained from a population that is normally distributed, regardless of the sample size. Yes. So let's write this down. So no matter what the sample size is, this will always be normal. And no matter whether this is normal, this will always be normal. The sampling distribution. Well done. Okay. The larger, who would like to give this a try?
Answer.
Okay. The larger
the sample,
yes, let's take a look.
the more accurate
the sample yes. Yes. So the larger the sample, the more accurate the sample mean will be as an estimate of the population mean. Yes. Good. The more variable the data, well, this is an interesting question. The more variable.
What does the more variable the data mean in this case?
The spread.
The spread?
This more variability, higher standard deviation, higher variance. If you remember, at some point in time, we compared McDonald's wait time with Wendy's wait time. And we said, I prefer Wendy's if I have to get fast food because the spread of the day of the time is less. So everything is closer to the mean, more condensed, more clustered around the mean. So the more variable the data, what do you think?
Less.
I think it's less because the wider, the more spread, the further away we are from the mean. Good. So let me stop sharing for a second and refresh your memory on that example. So we had McDonald's. It was something like this, if I remember correctly. and Wendy's was something like this. I mean, I don't want to give wrong impression that it's higher or lower, but see, the spread here is between, I don't know, what was it, 2 minutes and 5 minutes. But the spread here is the 95% is between 2 minutes and 15 minutes. So if I need to choose, if I have to choose, I would have to choose this because the spread is 2 to 5. But here the spread is 2 to 15. I'm exaggerating. I don't remember the exact data set. But it's potentially that I will have to wait 15 minutes or 14 or 13, but I would rather wait between 2 and 5. So this has more spread versus this. Okay, moving on. Let's look at this one and then we can, okay. So the standard deviation of the sample distribution denoted, yes, sigma of x bar, correct, is called the, so good. So let's discuss this. It's a good exercise. So the standard deviation of the sample distribution, it is denoted, it's called the population deviation of the, it's a very good, good question about the name of it. So the standard deviation of the sampling distribution x bar, yes, it's called it is sigma, so it's the population. It's not standard and it's not sample. Although we are looking at the sampling distribution, so the standard deviation is the sample of the sampling distribution. It is the population. Of course, it's not the variance or, but it is considered. It is considered as, it's not an error because we are going to talk about error later. It's a deviation. It cannot be distribution or mean. They're just throwing letters at us, words at us, and of the mean. Okay. So the standard deviation of the sampling distribution of x bar denoted sigma x bar is called the population deviation of the mean. It's sigma, so it has to be population. I'm thinking for a second about the sample. It's called the sample deviation of the mean. We're talking about the population. That's why we use sigma. Sometimes it is called a sample. So that's why I'm debating with myself. So standard deviation of the sampling, standard deviation, yes, of the sampling distribution. It is the population deviation, yes, of the mean. The sample distribution of sample mean, yes, it is sample, yes, but it's of the size and form, yes. I was debating with myself about the sample. The sample, okay, we know this. Yes, and it is the mean, yes. But it says 2 of my answers are incorrect. Why 2? Okay, they wanted a sample. Sample, yeah, they can call it the error, sample error of the mean. But the error of the mean depends on, and I'll explain this later. Let me just click on this and I'll show you. Yeah. Sample That's deviation of the mean. Sample. What do they want? I have no idea what they want. It's called the standard error of the mean. Yes, that's what I chose. So what does it?
You said sample error of the mean.
Oh, okay.
It was standard.
I did choose yes instead of yeah I did choose instead of standard error of the mean. However, let me explain one thing and I'll stop. So we're going to talk about mu plus or minus, or it depends. So z alpha that we're talking about. Now I have to be careful because z alpha in this book is considered to the right, but it should be to the left. So times sigma. So we're going to talk about the standard error of the mean. That's correct. But which they denote x sigma x bar as sigma over the square root of n. That's what we had. So that's what it is. That's the standard error of the mean. But normally the standard error, the words standard error, they are connected to a certain alpha that we just remember we had a few minutes ago, the z alpha. So it's connected to this, the standard error. But they want to call it the standard error in this book, that's fine. That's fine too. But it's normally connected to a particular alpha. So alpha is level of confidence, which we will talk about a lot very soon. Level of confidence. Confidence level. This is what alpha is. So that's when the standard error comes into play. But they, in this book, I'm learning also, they want to call it standard error of the mean, which is fine, acceptable. I just want to try this again to look at the okay, I see what I did. It is okay. Now I see what they want. Standard deviation of the sampling distribution denoted yes, it's called the standard error of the mean. Fine, I'm okay with that.